Safety Essentials webinar. All of PGE's seminars and webinars are in part sponsored by the Energy Trust of Oregon and the Northwest Energy Efficiency Alliance. They work together to make sure the concepts and recommendations you learn in the events are consistent across all of the individual programs and services. So thanks for attending today. I appreciate the opportunity to be here today and talk about electrical safety essentials, how to protect personnel and comply with mandates. Beth gave you a little bit of my background, which we'll touch on, but for today's agenda, we'll provide an introduction to electrical shock and arc flash hazards. So we're going to talk a little bit about arc flash and shock hazards, and again, this is just a short introduction. There are other hazards that are present when performing electrical work, such as falls, confined space work, chemicals, etc., but those will not be discussed today. We're going to discuss exposure to hazards and the risk of injury, and we're going to touch a little bit of both exposure to hazards at home and at work, because I care about whether you are involved with the electrical incident, whether it be at home or work. We're going to introduce you to a few of the OSHA requirements for electrical safety. And we're going to introduce you to the 70E standard, National Fire Protection Association standard for electrical safety in the workplace. We'll discuss steps to reduce risk of injury. And of course, this is not a complete electrical safety training course. This is just a brief introduction to electrical safety. For folks performing electrical work or working on energized or near energized equipment, generally it takes about at least an 8-hour class to cover all the content necessary to help folks understand the hazards and protection and requirements, etc. So just a little warning, by the way, these slides may contain graphic material, so some of the slides will have some material in here. We have some pictures in here that are a little on the gruesome side for some folks, so just be forewarned on that. So Beth gave you a little bit of introduction on my background. I am really focused and passionate about electrical safety. I've been involved with the electrical industry for over 25 years, and 20-plus years ago, my level of passion stepped up on electrical safety when I was almost killed. I was hung up on electricity and shocked, but not only shocked, I was hung up. I could not let go because of a poor installation that caused me to get stuck up on a ceiling until I passed out and fell 8 feet to the concrete. So the fall actually is what saved my life. And in fact, the doctor that performed the EKG said it was probably the bounce off the concrete that restarted my heart. So with that, and a couple arc flash, where we have had electrical explosions. So I've seen 2 arc flash events, been involved with 2 arc flash events. One was an improper installation. Another was just a defective, brand new, but defective piece of equipment that exploded. So I've experienced both electrical shock, near electrocution, and 2 arc flash incidents. And I've survived, and I'm still here to talk about it. So my goal is to help people not have to go through what I've gone through. So what I'd like you to do is, if you could tell me a little bit about yourself, if you could use the webcast tools to indicate maybe your job function. So in other words, if you could use right up here the X mark and just click in here what type of job function you have, that will help me know a little bit about the background of the audience that I'm working with. Great. So we have some folks in facilities, some folks in energy efficiency, engineering, and consulting. Great. I appreciate that feedback. So thank you very much. Okay, so we're going to start out with electrical hazards and potential impacts. So with that, let's move forward. Let's look at electricity. Typically, exposed energized electrical equipment doesn't look or sound very intimidating or threatening. We need to treat with respect and follow safe work practices of any electrical installation, whether it be open, and I have 3 different examples here that I put on the slide. Here is a piece of electrical equipment. This is actually what's called a unit substation. It's a transformer stepping voltage from 12,470 down to 480 volts, but notice all the vent holes that we have at the top and bottom. Now, a lot of times when we think of electrical equipment, when the doors are all closed, we don't necessarily think of it being a hazard. And the risk of a hazard is much lower when the doors are all closed. But that doesn't mean that there is no hazard whatsoever. We've had several cases where, whether it be contamination, a damaged part, or a rodent getting into electrical gear, that we've had explosions take place. And as you can see from all the vent holes on the top and bottom of this equipment, that gear is not going to contain the arc flash incident energy level. Now in the middle picture here we have exposed bus work. So this is a grounded surface right here, part of the switchboard, and right here is the exposed bus bar, 277 volts to ground, 480 volts phase to phase. Definitely a hazard when energized. And of course, we have overhead lines here, where if we get too close to those overhead lines, or we make contact with those overhead lines, whether it be bodily contact or with some type of conductive material such as a wet 2x4, tree branch, etc., we can definitely experience the wrath of electricity. Now, down in the lower right-hand corner, you see the dog there. And the reason I put the dog in this picture is because a lot of times around electricity, we get what I would call a little bit complacent. It's easy to not think of electricity as being harmful, especially if we haven't seen, electrical incidents, if we haven't experienced them. But yet, what I suggest to people is, if you were to go down the street, and let's say you were going to open up a gate to go to a neighbor's house, and you put your hand on that gate, and all of a sudden a Rottweiler and a German Shepherd, and I'm not picking on those dogs, but people typically think of those as being a little bit more ferocious if they look angry as compared to, the smaller dogs. Now, I was a paper boy, so I've experienced the smaller dogs. They were usually the ones that latched onto my ankle. But let's say a Rottweiler and a German Shepherd or a Doberman, they're growling at you and they look like lunch. They look at you like you're lunch. Would you just walk inside the gate? Probably not. In other words, you'd respect the energy there, and you'd maybe call the owner and ask the owner to lock those dogs up. And that's in the electrical industry what I would call control of hazardous energy, or lockout, tagout. So in other words, you would have total respect for those dogs. But on the flip side, a lot of times when we look at electricity, we may not give electricity the same level of respect. In other words, we may open up an electrical cabinet with energized equipment and not necessarily say, okay, wow, that could really be hazardous to my health. That could harm me. And so when I talk to people when I do training, what I suggest is I want them to think in terms of the fact that whenever you open up a cabinet and the equipment's energized, you could be harmed as much, if not more, than if that dog was inside the gate that you were walking into. So when we look at shock hazards, National Safety Council, approximately 30,000 non-fatal shock injuries each year. 30,000. Approximately 1,000 fatalities each year due to electrocution, with over half of them while servicing energized systems less than 600 volts. So a lot of times people say, well, hey, it's just the big stuff. No, less than 600 volts, over 1,000 fatalities each year. Electrocution, by the way, is the 6th leading cause of industrial fatalities. 6th leading cause, still up there at the top, and it still remains one of the top causes of industrial fatalities even after all the implementation of safety measures that we're starting to see in the industry. Now, in the upper right-hand corner, you see a picture, someone working with, the wires going to a lighting fixture. Okay, this is one of the areas we see a lot of injuries in, lighting fixtures, lighting ballast replacements, upgrades, etc., because sometimes people don't understand the level of shock that can occur with those and don't necessarily take the same level of precautions. The picture just below it shows a picture of someone that actually has had electrical contact burn. This is not from an arc flash, but this is from electrical current flowing through their body because they got stuck on electricity. And as the current flowed through their body, it actually caused part of their skin and the underneath that skin, excuse the expression, to actually cook. Okay, so this contact burn caused severe injury to this person. So when we look at shock hazards, it doesn't take a lot of current to create a significant shock hazard. So when we look at just a faint tingle there, okay, 1 milliamp, that's 0.001 amps. Very little current flow here at 1 milliamp, just a faint tingle. 5 milliamps, just below it, slight shock felt, disturbing but not painful. Most people can let go. However, strong involuntary movements can cause injuries. So this is the level at a typical GFCI, ground fault circuit interrupter. So if you were to look around your kitchen sink, hopefully you have these receptacles installed. They have 2 buttons on them. One's a push to test, one's a reset button. And by the way, these are designed to be tested monthly. But if those are installed properly, they are designed to trip between 0.004 or 4 to 6 milliamps, 0.004 to 0.006 amps of current, 4 to 6 milliamps. And that's this level, slight shock felt, disturbing but not painful. Most people can let go. However, strong involuntary movements can cause injuries. Okay, so this is the level. We want these GFCIs, by the way, we want to use them on portable cords, and it's actually mandatory in many cases. OSHA in general, their General Utilization Standard 1910 Subpart S actually calls for the use of GFCI protection anytime we're using portable cords or tools for construction type activities. The National Electrical Code also calls for these in many locations around homes, businesses, rooftops where there's a higher potential for exposure to electrical shock. So going down the list here, 6 to 25 for women, 9 to 30 for men, painful shock, muscular control is lost, and this is the range where freezing currents can start. In other words, we talk about freezing currents. In other words, your muscles may lock up. You may not be able to let go. Down below that, we see 50 to 150 milliamps, extremely painful shock, respiratory arrest, breathing stops, severe muscle contractions. Your flexor muscles may cause you to hold on, or your extensor muscles may cause intense pushing away. So maybe the pushing away is good because you push yourself away from the electricity, but if you fall off a ladder and knock your head on the concrete, that's not a good thing. And of course, we can see down below it only gets worse. Between 1 to 4.3 amps, ventricular fibrillation. In other words, when the current flows through your body, that current causes voltages in your body, whether it be your lungs, whether it be your muscles, whether it be your heart muscle, is controlled by electricity, electrical signals being sent from your brain. So when we have an outside source of current flowing through our body, it creates voltage signals which interfere with our body's normal signals. By the way, if you get a significant shock, will you please go get that checked out? A lot of organizations have policies to where if you get a significant shock, that it's mandatory you go get checked out. Several people have died hours later. Sometimes they die right when they get shocked, but sometimes we have people die hours later or into the evening because of the impact of their body from electrical shock. And of course, we see down at the bottom, we haven't even tripped a standard residential breaker, let alone a commercial breaker. So the lowest overcurrent at which a typical fuse or circuit breaker in a home opens is 15 amps. So again, shock hazard takes very little current to cause major damage. So when we look at the exposure for electrical shock, it's those who perform work on or near energized equipment can be exposed to it, those who use electrical tools, equipment, or appliances, and shock can occur at home, work, or play. So on the far left there, we see a picture here. Again, this is a picture I showed you before, where it's obvious we can have direct contact if we're working here with the bus work inside. In the picture here, next one over, we see someone using portable cords and tools. In other words, they probably have a cord hooked up to that portable drill. A lot of people get shocked by using portable cords and tools which have damages to the cords or defects. Again, the importance of using GFCIs to help protect against shock can't be overemphasized. And of course, we have all kinds of new technologies here. We have adjustable speed drives that we work with. We have photovoltaic systems and inverters associated with those systems. So as we bring new technologies on, there's a learning curve around how to work with those technologies, what the exposure is to those technologies. And so we have technicians that are out working on those things that may not fully understand the hazards around electrical shock or may not understand safe work practices. So again, it's very important that we understand the types of technologies and the equipment we're working with, and we get educated on these things and follow safe work practices. So I've just given you a couple examples of exposure here on the next slide, and you can see the slide here where we have the damaged equipment. So this is at a resort in Eastern Oregon where the raceway coming up here, the metal raceway is broken. The whole junction box there is broken. So the ground path is totally disrupted. There is no equipment grounding going on there. So if someone comes up and there is a fault, one of the energized conductors makes contact with that conduit, there is no fault return path back. That whole system would stay energized. And of course, up here we see that the cord is damaged. One of the big shock hazards here, we see that the cord is damaged as well, the connection to the cord cap. And this is another big one where we have a three-prong cord or three-prong device, let's say a drill that uses a three-prong cord, where the third prong, the ground, equipment grounding conductor is missing. These are also very, very important items that we check on our cords. If that ground pin is missing or not functioning properly, we're definitely presented with a major shock hazard. So we also have overhead lines. So contact with overhead power lines can be deadly, and it doesn't even take direct contact. Even getting close enough to the overhead lines, there is enough voltage on many of these lines where it will find you. If you get close enough to the lines, it will arc over to you. So we have Oregon OSHA Subpart S and the Oregon Administrative Rule 437.002. 0047, working your energized overhead lines, okay, that deals with what we call working clearances. So they talk about the minimum working clearances, and the minimum they're calling for is a 10-foot clearance up to 50,000 volts and greater clearance above 50,000 volts. So I'm going to ask you to see the OSHA and Oregon OSHA, and when I call out WAC rules, if you see the term WAC rules in the slide, that's the Washington equivalent, okay, Washington's rules. So for their Washington Industrial Safety and Health Act. By the way, I will give you links in this presentation, and Beth will be sending you the presentation with the link. So any links that we have in here, you'll get a copy of the presentation. So again, OSHA is calling for a minimum of 10-foot clearance. I'm going to ask that you consider applying for or working with 20-foot of clearance, because sometimes it's hard to judge. 10 foot isn't that much, and it's easy to get something in your hands to get closer, a ladder closer, maybe a painting pole closer, that you make sure that folks understand overhead lines. Also, any kids, grandkids, you know, spouses, significant others, please make sure they understand that. Not everybody understands what goes on with electrical systems and the exposure that they may see. So what I'm going to ask you to do is to, again, look at the links that I give you later on in the presentation. Also, please refer to PGE's safety webpage, okay, at portlandgeneral.com/safety, as Beth mentioned earlier. So I'm going to ask for a little bit of feedback. I've been shocked. I've been hung up before. Have you ever been shocked? Would you take your tools up here and just mark maybe how many times you've been shocked for me? Now, a lot of times when I teach classes, what I'll see is that folks usually have been shocked at least once. And I see a few nevers. So thank goodness that you've never been shocked. But folks that have been shocked once, you probably know that maybe it hurt a little bit. But being hung up is a whole different level of pain, okay? And never, good. I'm glad to see there's a lot of nevers here. Because some folks have been shocked once. I have several people that have been shocked twice or more, especially when I teach classes, you know, with electricians and so forth. And sometimes they say, well, you know, I made it through, I survived, but the next time you may not survive, okay? You may get hung up on the electrical system and may not be able to get free. And it may be severe injuries, or it may even result in death, okay? I've had a lot of people in my classes that have been hung up on electricity. Great, thank you for the feedback. Again, I'm glad to see a lot of nevers there, but I see some folks that have checked once. And since I've been hung up on electricity, I haven't been shocked since. So, but again, we want to pay attention that we never get shocked, because it may end up meaning that we get hung up. So let's focus a little bit also on arc flash hazards. Okay, so 5 to 10 arc flash explosions occur in electrical equipment every day in the U.S. 5 to 10. Wow, that's a lot. So this picture here in this slide is from a friend of mine in Ohio. Okay, and he opened up this 600 amp fusible disconnect here, and that fusible disconnect, when he opened up the disconnect, he was wearing all natural fiber clothing. The arc occurred on the primary side. In other words, you think 600 amps isn't that much, but yet it is. But you say, well, why didn't the fuse just blow right away? Because the arc occurred on the incoming side to the fuse, okay, and actually the arc went around the edge of the door, it blew a hole through the door, and it blew the door open. Okay, so this arc did cause him to get some level of burn. So sometimes even with switching systems or operating systems or racking breakers in and out, we can incur exposure to arc flash hazard even though we're not opening up the gear and working on it directly. So it's very important that when we look at our safety programs and policies that we have a job hazard risk analysis in place. In other words, we're thinking about the hazards, we're paying attention to the potential hazards, and we're providing the appropriate steps to avoid or eliminate those hazards or to protect ourselves against those hazards. So when we look at arc flash and blast, arcing faults release dangerous levels of radiant heat energy capable of causing severe burns or fatal injuries. We also have the blast pressure wave, and that pressure wave can be up to 2,000 pounds per square inch. So in a nutshell, when we have this blast pressure wave, not only does it spread the arc over a wide area, but also it can create internal injuries from the blast pressure wave. In other words, if we get hit with this big blast pressure wave, it can cause an internal injury, and that's why we limit how much energy we expose ourselves to. Electrical PPE will help provide protection against the heat, okay, if we properly select it and apply it, but will do nothing to protect against an injury from the internal injury from the blast pressure wave. Also, when we look at the blast pressure wave, there have been several cases where people have been blown back and they end up falling and hitting their head or falling across something and suffering an injury because of that. So one of the key things here too is to respect it, understand what can happen, and to again avoid the hazards, including looking behind you. If an arc is to occur, where might you fall? Where might you be blown back? What might you fall into? So we've got workers that have been thrown across rooms and knocked off ladders. In some cases, again, the blast pressure wave has created massive internal injuries. Other injuries include hearing loss, lung damage, damage to eyesight, physical injuries, and more. So what I'd suggest, if you haven't seen arc flash or blast, you can go to YouTube and just type in arc flash or arc blast, and you'll see a whole host of videos that come up that deal with arc flash and blast events. And this picture that in the upper right-hand corner is just it's a snapshot out of one of the pictures where folks received, you can see the folks being blown back there. They're kind of mid-air there, being blown out of the switchgear during an electrical arc event. But again, I would highly recommend going to YouTube and typing in arc flash and looking at some of the videos. So when we have arc flash hazards, we have the temperature of an arc flash. Arc terminal is 35,000 degrees versus the surface of the sun at 9,000. 35,000? Yes. In fact, that's actually been measured in arc testing labs at the source of the arc. Versus the surface of the sun? I'm not sure who took that measurement. One of the classes I was teaching said it was an apprentice, and they've never seen him since, but hopefully not. So metal droplets coming off the arc, 1,800 degrees. Clothing ignition can occur between 700 and 1,400 degrees. Burning clothing can burn upwards of 1,400 degrees. Now compare that to with what your skin can handle. A curable burn for 1/10 of a second, 145 degrees. Cell death, 205 degrees. You can see there's a big difference between what your skin can handle and what's coming off the arc. So when we look at arc flash hazards, a few of the causes include worker error. Maybe somebody drops a wrench. Maybe somebody, reaches in and touches something. Again, there's all kinds of things that people can make mistakes on. Even experienced people make mistakes. Now, I ask folks in my classes, when was the last time? You may have driven for 20 years or 15 years, but I'll ask them to think about, when was the last time you drove through an intersection only to look in the rearview mirror to see, was that light red or green, or was there a stop sign there? And it's amazing how many people say that sometime in their driving career that they've done that they've driven through an intersection and they weren't sure whether the light was red or green. Okay? We can have damaged equipment. So that was one of the incidents that I experienced was an arc flash from damaged equipment. We can have defective equipment. Okay, or lack of maintenance sometimes if we're not maintaining our systems, improper maintenance, contamination. We can get, I've got one site where they've had several squirrels get into, and again, sorry about the illustration, but squirrels and rats and so forth get into the switchgear. Improper use of equipment can also create arc flash events. In my case, the second arc flash event, or the first one I went through, was actually due to an improper installation. It was a poor installation that after it was discovered, after it caused the arc flash for me, the owner of that facility actually went in and took that installation out and corrected it. So when we look at impacts and liabilities of an arc flash incident, the victim may not return to work, may have permanent psychological damages. These can be very painful injuries. And the expense of a worker being off for a week, according to the risk and loss prevention folks that I talk to, can range from $20,000 to over $100,000. So you can see that we're talking about a significant amount of money, plus a worker can be impacted for the rest of their life. They may not even be able to come back to work. So an effective safety program is an investment. So let's touch on safety codes and standards here and take a look at the safety codes and standards. So proper installation and maintenance of the electrical systems and equipment is essential for a safe facility and environment. Okay, so these systems need to be installed properly, and I've given you some references there. NFPA 70 to the National Electrical Code. Of course, the OSHA requirements we need to meet, both from installation requirements and safe work practices, and we need to meet the NESC for outside overhead lines, transmission and distribution equipment, or cogen equipment. We have NFPA 70B for maintenance, and you can see the list here, and again, Beth will be sending you the slide. So you can look up these standards and codes and then look at the installation and maintenance requirements. So just going over an example of the importance of safety codes here, we see that this Green Beret, and I hate to use this as an example, but I've got several examples across the U.S. I could give you, hours of examples. Here's a highly decorated Green Beret, Staff Sergeant Ryan Masseth. He died in the bathroom. Okay, he reached up and he touched the handle, the shower handle, and the water pump that was feeding the piping system that fed the showers was not properly grounded and was not properly bonded, and he was electrocuted. He died in the bathroom. Just a few weeks ago, I had a gentleman in my class that was climbing underneath his house, and he talked about how he put his hand on a pipe and he received a shock. And when I talked about this, he goes, I thought that was okay, that was normal. He goes, I just thought I shouldn't have touched the pipe. And when I said to him, no, you have a fault in your wiring system somewhere and your water piping system's not properly bonded. You need to call your folks, your electricians, and get them to your home right away and tell nobody to get, nobody gets in that shower, nobody uses the water system until that's corrected. So it's very important we follow safety codes to avoid things like this. We have NEC, National Electrical Code violations. Again, another violation is a circuit breaker may not be rated for the available short circuit or fault current. This occurs quite frequently. In the power system studies we do, looking at arc flash, a lot of times we have what's called underrated circuit breakers. So breakers not rated for the total amount of current that could flow through them during a fault condition. And if that occurs, this is the outcome, the potential outcome, where the breaker can actually explode or be significantly damaged, and again, not protect the personnel, in fact, cause significant exposure to hazards. So we have wiring, grounding, and bonding errors, and I mentioned a gentleman with his home. So where we have wiring errors, I gave you an example too in the lower right-hand corner here, where we have a wiring error here where the junction box is broken apart. So whether it's a cord that's missing a ground pin, whether it's a ground wire that's missing, whether it's a conduit that's broken apart, any type of grounding and bonding errors that are in the system that are NEC violations can actually cause safety hazards. So we can see this person here on the left. They can become a parallel path for current during a fault condition if my proper grounding and bonding, or my grounding and bonding is improperly installed or damaged or makes a bad connection or over the years is corroded or rusted, etc. And these are fairly frequent out there in electrical installations. Okay, so let's take a look at OSHA. So electrical safety and arc flash, OSHA regulations are developed to mandate that employers provide a safe workplace for their employees. We're just going to touch on a few sections of the standard, 19, 10, and 26. And again, here's a link to OSHA.gov. That's federal OSHA. In Oregon, we're under Oregon OSHA. So we see there's a link there to OSHA.org. Okay, so the state of Oregon has its own program, and I've given you the link as well to Washington's program. So the state can modify federal OSHA requirements, but all states operate underneath federal OSHA requirements, kind of underneath federal OSHA's umbrellas, but they can also take and enhance or add to the requirements of federal OSHA, and the state of Oregon has done that in many sections in the OSHA requirements. So we're just going to review a few sections of the OSHA standards that deal with electrical safety. Of course, there's many, many more. So we have OSHA 1910, Subpart I, deals with personal protective equipment. Requirements, use, and training. We have general environmental controls, and Subpart J gets into general lockout, tagout, color coding of signs. Subpart S deals with electrical wiring, work practices. Now this is one of the core areas for electrical safety, OSHA 1910, Subpart S. So if you go to the OSHA website, you can look up 1910 Subpart S and see the electrical requirements. We have power generation, transmission and distribution in 1910 Subpart R, and of course 1910 Subpart K deals with safety and health regulations for construction. We also have in the industry NFPA 70E, Standard for Electrical Safety in the Workplace. Okay, so we're going to touch on a few elements out of Chapter 1, work involving electrical hazards, but this is a reference that OSHA uses. A lot of folks in the industry use the NFPA, National Fire Protection 70E, the Standard for Electrical Safety in the Workplace. OSHA also references this document. They don't mandate that you use 70E, but they also reference this document in providing information that could be helpful in complying with the OSHA requirements for electrical safety. Now, the annex in this document also includes reference publications, helpful information, examples, sample procedures, documents, etc. If you do not have a copy of this, I would highly recommend going to nfpa.org and downloading a copy of that. Of course, it is for sale. You can access it to review online, but you have to, if you want a copy of it for your own use to print and review and to print out, you do have to purchase that document. So, what can we do to help prevent injury? Let's look at electrical safety training. Personnel who perform work on energized equipment or those who are exposed to electrical hazards, those who even use electrical tools, equipment, or appliances, anybody that's exposed to potential shock. Now, the training has to be relative to what folks do. In other words, if folks are only using cords and tools, they don't need to have an 8-hour training course, but they should understand how to basic cord and portable tool safety, make sure the ground pin's there, proper use of GFCI. Now, in the upper right-hand corner, we can see here OSHA they have a requirement. They have training requirements for and typical occupational categories of employees facing a higher than normal risk of electrical accidents, and they've given examples of folks that they call out for specific training. In other words, these folks, they say, have a higher than normal risk of electrical accidents and need a level of training. So we can see here, we even have painters, for an example, on that list because they can be exposed to overhead lines or electrical equipment. So training is one of the ways that we can help avoid injury. Okay, when we look at OSHA Subpart S, qualified person, we could see that one who has received training in and has demonstrated skills and knowledge in the construction and the operation of electrical equipment and installations and the hazards involved. So, note 1 to the definition of a qualified person, whether an employee is considered to be qualified will depend on lots of circumstances in the workplace. So in other words, you can be qualified for some pieces of equipment, not for another. I would highly recommend, again, that you go to the OSHA and look at the full definitions and the training requirements for a qualified person. But notice up there at the top, I've underlined one who has received training in and has demonstrated skills and knowledge. In other words, can that person demonstrate not only that they have received training, but they can apply, that they know the information, how to apply it to keep themselves safe in the workplace. Okay, so let's look at use, inspection, and maintenance of equipment. So checking cords, outlets, electrical equipment for damage, wiring errors, and again, the use of GFCIs, I cannot emphasize enough. Now, that provides protection for low-level shock hazards. So in other words, at very low levels of current, that protects, it trips, should we have someone that gets between an energized conductor and the ground, whether that be the ground you're standing on or a ground wire. But I can also tell you, though, that there are limitations to GFCIs. They do not protect personnel against getting shocked, let's say, line to neutral or phase to phase. It's very important, though, that we check our receptacles, we make sure our GFCIs are working properly. In the upper right-hand corner, too, you can see someone using a receptacle tester to verify that the circuit is actually wired properly and that the GFCI is tripping when it's supposed to trip. Very important that we check our receptacles and cords against wiring errors, loose connections, bad grounds, etc. So here, again, another slide showing the cords and adapters that sometimes get used. In the upper right-hand corner here, we can see that there's a 2-wire extension cord, no ground wire. So in a nutshell, there's no ground in this cord. The equipment should have been designed to work with this cord, be UL listed for it or ETL tested to the UL standards. but it's important that we don't use 2-wire cords on devices that need a 3-wire cord. And it's also important that we make sure that, in this case, we have a ground pin missing. It's a hazard. Or here we have an adapter. Some of the older homes do not have ground wires, and people sometimes apply the adapter, but if they do not bend this tab down and connect it to a screw that's connected to a grounded outlet, this is a safety hazard. Even though you connected it to the screw, you have to test and make sure this is connected to a grounded outlet. So again, it's very important that we follow safe work practices in the use of cords. A lot of people get shocked and killed on with the use of portable cords and tools. So it's also important that we pay attention to product defects, whether it be, in this case, a surge suppressor that's catching on fire, whether it be a meter. So in other words, if you're using test equipment to meter, to measure voltages, or to verify lockout, tagout, there are a lot of meters that are under recall. When is the last time you checked for your meter to see if it's under recall? So I've given you the website here, cpsc.gov. And again, Beth will be sending you a copy of the slides so you can get that link. Okay, so reclosing breakers. So a lot of times we'll have folks that will reclose breakers. So a breaker will trip and they'll reclose the breaker. Okay, so they'll go up and reset that breaker. Okay, now if you have not tested to the circuit to verify that it's safe to do so, that's actually against OSHA regulations. So in other words, if a breaker trips, what they're saying is if it's an overload, in other words, you plug too many things in or a motor jammed up and you cleared that and you know it can be done safely, okay, then it's okay to reset that breaker. If you do not know the cause of that breaker, or if you had a fuse blow, they're saying you cannot just go in there, put new fuses in, and reclose the fusible disconnect or close the breaker. A little example of a place I was just teaching at here recently, the gentleman had a 1200 amp breaker trip. He went up to the breaker and he actually reset the breaker without doing any investigation. It blew about a 12-inch hole in the front of the switchgear and narrowly missed, causing extensive damage to his body. So you can see that sometimes when we close breakers, so repetitive manual reclosing of breakers is prohibited. And if you look at the UL listing on a lot of the breakers, a lot of times they're only tested at UL to trip 2 times at their fault current rating. Okay, so in other words, if it's tripped twice at its full fault current rating, then the breaker should be replaced. So responsibilities, when we look at NFPA 70, they call for safety-related work practices to be provided by the employer, safety-related training to be provided by the employer, but then which is implemented by the employee. So we have responsibilities on both sides. Both the employer has responsibilities and the employees have responsibilities for an electrical safety program and the implementation of that. And a lot of times in organizations we have folks that have to cover a wide variety of safety, fall protection, chemical, etc. So it's very important that we have folks that understand electricity that help out those folks in the organization to look at the hazards and coming up with safety program, safety policies, etc. that, you know, are very important to their organization and their work practices and their work sites. So an electrical safety program, 70E calls for the employer to implement and document an overall electrical safety program that directs activity appropriate for the electrical hazards that are present, the voltages, the energy levels, and the circuit conditions. And safety-related work practices are one element of an overall safety program. In a nutshell, our safety program should be designed to where a lot of what we're doing is actually trying to design out exposure to the hazards. Not just putting on personal protective equipment and saying, okay, I've got the PPE on, I'm okay to work on this energized, but actually trying to figure out a way that I don't even have to be exposed to the hazards. Okay, and I've given you an example here in the lower right-hand corner. And this is from, it's courtesy of Grace Products, but they make all kinds of external ports. There's other manufacturers that do the same. But sometimes this one has a switch on the outside, and you can see a port there for an RS-232. A lot of times these have Ethernet ports. So in other words, if you're always opening up a cabinet and you're exposed to 480 volts exposed buswork in that cabinet, but your primary purpose is to plug into the Ethernet port into the PLC, why not put the Ethernet port outside the equipment so that you never have to open up the equipment, you never have to be exposed to the 480 volt to plug into the PLC. So an example there where now we don't have to PPE up. There may be a slight cost associated with retrofitting of the equipment, but think how much we're going to save in productivity and exposure for folks working on electrical systems. So again, an example there of looking at an electrical safety program, not only PPE requirements, safe work practices, but how do we eliminate or reduce the hazards or the risk folks will be exposed to. Lockout, tagout. OSHA says that equipment must be de-energized before work is performed. So if we look at 1910-333A1, it states, live parts to which an employee may be exposed shall be de-energized before the employee works on or near them unless the employer can demonstrate that de-energizing introduces additional or increased hazards or is infeasible due to equipment design or operational limitations. Now, to give examples of that, again, I'm going to ask you to visit the OSHA website or OSHA or the LNI website for Washington, because they give examples for exceptions to that. In other words, where energized work is considered justified. So you can view those online, or if you have questions, you can ask for us to send you a copy of the OSHA requirements, but I would highly recommend you go to the OSHA website. In a nutshell, they're saying turn it off. Unless there's justification, unless you're going to create an additional hazard by shutting it off. So let's say you're in a big chemical plant and you shut off a power system feeding the chemical vat, gas detection systems and alarms. That could create a greater hazard. But the challenge here is I was commissioned several years ago to do a study on the #1 cause of unplanned downtime. And what my findings were, and it could be different than it was several years ago, but at that time, the #1 cause, at least from my study, of unplanned downtime in an electrical system was electrical folks working in or folks opening up and working in the gear. In other words, it may be a loose connection that's been working, but you disturbed the loose connection. So if it's too critical to shut it down, and we have to work on it energized, just remember that by us working on it, we're raising the probability that we may have a shutdown. So OSHA also says if equipment cannot be de-energized prior to work, employees must be properly protected. So when employees are required to work where there's a potential electrical hazard, 1910-335 calls for the employer to provide electrical protective equipment that's appropriate for the specific parts of the body to be protected and the work to be performed. You say, well, they're not telling me specifically what to do. You're right, they're not. But they do reference, OSHA Subpart S references NFPA 70E, the standard for electrical safety, which says it can provide information that can be helpful in understanding and complying with these requirements. So in a nutshell, they're giving you leeway to come up with a game plan. They're pointing you towards a national industry consensus standard, but you also have flexibility in what you can do. I would highly recommend, again, getting a copy of the 70E standard and learning it. And don't just casually implement it. Don't just take some of the tables out. It's very important you understand the standard before you implement it. Now, there are some cases where we could follow 70E, and if folks still get hurt, we could possibly be cited. Why? Because, again, when you look at any safety program, it requires job hazard analysis. It requires folks having knowledge and implementing that knowledge to take the necessary steps to protect themselves. So, Subpart I with OSHA deals with personal protective equipment. Employers are responsible for performing a hazard assessment, okay, and it states the employer shall assess the workplace to determine if hazards are present or likely to be present, which necessitate the use of personal protective equipment. So in a nutshell, they're calling for you to assess the hazards and to determine what hazards are present and then what type of PPE will protect folks against hazards. And again, the best approach is to avoid the hazards to begin with. So designing hazards out of systems, whether it be retrofitting equipment or new installations, we want to try and avoid the hazards. But we also need to protect folks with proper personal protective equipment against shock and arc flash hazards and any other hazards that may be present when we're doing electrical work. So again, you can look this information up and get it in full detail on OSHA's website. Again, you're probably going to have to refer to additional information outside of OSHA when you're looking at arc flash hazards such as NFPA 70E. So, if the hazards are present or likely to be present, the employer shall select and have each affected employee use the types of PPE that will protect the affected employee from the hazards identified during the assessment, communicate those decisions, select PPE that properly fits, in other words, size 4XL or 5XL doesn't work for everybody, okay, and provide training and documentation in the selection, application, and use of PPE. And again, folks should have demonstrated knowledge that they can show that they know how to pick and use their PPE. So NFPA 70 and OSHA, they talk about risk assessment and hazard analysis. Now 70 will say you can do a study where you can actually calculate the incident energy level. You can put labeling up, and so you can come up with a shock hazard and the boundaries, the arc flash hazard boundaries, the risk hazard reduction strategies, equipment labeling, electrical PPE requirements. So these are all parts of a risk assessment and hazard analysis as discussed in OSHA and NFPA 70E. Okay, if you don't have the time or the money or not prepared to do, have a study done on your electrical system, NFPA 70 also gives you guidance using what's called the table method. So in other words, they give you tables that allow you to see the types of PPE that they recommend. It's very important you understand the limitations in these tables and how to properly use them. If you look closely at the tables, you can see that there's some limitations. In other words, I have to find a table that matches up with the location I'm working at. I also have to make sure that the parameters that they provide in the table here, I do not exceed those parameters. In other words, they give a maximum short circuit current and breaker clearing or protective device clearing time. They also give you working distance, which is very important because if you work closer, you can have a much higher exposure to the incident energy level. In other words, your energy level typically goes up. If you cut your working distance in half, the energy level you're exposed to typically goes up by a factor of 3 to 4 times the energy level at 18 inches. So information is available in 70E that gives you a task-based, a table method to pick your electrical PPE. It's a great starting point. Okay, there are many other important items within NFPA 70 and OSHA requirements that we don't have time to go over today, but whether it be energized work permits, in other words, proper planning and justification for doing energized work, job briefing, risk assessment, insulated tools, current test equipment, meaning current safety standards, and I could just go on and on. There's just too much to cover in a webinar, but again, I'm directing you either to the OSHA site or NFPA 70E will be great places to start. So when we look at a few key elements on electrical safety program, we're going to send out kind of a self-assessment checklist, and Beth will send that out to everybody after the webinar. Okay, so you can kind of do a self-assessment, and I've kind of given you a list, a checklist here to see where you're at with your program. So you can look at your overall electrical safety program, and this isn't covering everything, but it's kind of a quick checklist to let you to do a self-evaluation to see where you're at with your program. So just a little feedback, a little quick survey here. Where are you at with your program? If you could just kind of check maybe in a box here of where you currently sit with your program, your overall electrical safety program, just like to see feedback from the industry. And I see a wide variety of folks across the industry as I work with different organizations. Even some very large industrial organizations are just getting started with their electrical safety program. Okay, so I see some are just starting, some in great shape. Great. Okay, so appreciate that feedback. Need help? Okay. So it's pretty typical that we see folks in a wide spectrum. Some folks just getting started, and it can be overwhelming. Just remember, one step at a time. Start with the OSHA requirements in 70E, and we'll talk about some resources here. So thanks for your feedback on that. So here are a few industry resources. Again, Beth will be sending these out, but we have the Oregon OSHA or the Fed OSHA website. Again, I gave you a link early on for the LNI if you're from Washington or you work in Washington. They have some requirements that differ from Oregon OSHA requirements. We have the link here to the NFPA.org for the Standard for Electrical Safety in the Workplace. We have the Electrical Safety Foundation International. And of course, PGE also has some guidance and some information on safety, especially when we get into overhead line safety. And there is an upcoming half-day safety awareness training that PGE is hosting for supervisors, managers, and environmental health and safety professionals. That's an introduction to electrical safety. PGE is also sponsoring a full-day training for folks that are working on or near electrical equipment, such as engineers, electricians. It's great for safety personnel as well to see what their folks have to deal with in the field and to help be able to structure a program. And there's industry trainers and consultants that are available as well to help with getting going or establishing or updating your electrical safety program. So recap, electrical shock and arc flash hazards can cause serious injury or death. Electrical safety is taking the necessary steps to avoid worker injury due to hazards. Injuries are preventable. Resources are available. So it would suggest developing a game plan. Even if you haven't started, start today. Make a decision to start today. It will take time, but start making progress towards a goal. Put together a game plan. So when we look over here on the right side, we can see that we don't want to just, we may start with personal protective equipment. In other words, it may be our starting point here. We may start with PPE, but typically we're going to have a mix. In other words, this is kind of going from the most effective up here, elimination of the hazards, to what's called the least effective. This is the hierarchy of health and safety controls, kind of shown in the order from the most effective to the least effective. Our goal is to eliminate the hazards, but typically in many facilities we're going to have a combination of these items, ranging from items 1 through 6 here, that we implement to help prevent personnel injury and exposure to hazards. So I want to take this just a minute to thank PGE and the Energy Trust for having this webinar, sponsoring this webinar today. And with that, I'm going to pass it back to Beth, and she is going to take any questions that you may have, and she will ask me those questions. So thank you very much. I appreciate the opportunity today to provide this training.
Thank you, Gary. And I wanted to let you all know that we also have additional energy efficiency resources. PGE and Energy Trust provide free consultations by phone or on-site to help you identify energy-saving opportunities at your facility. And if you're interested in contacting someone, we have the phone number here and email for Paula Conway for commercial customers, and for our industrial customers, you would want to contact Darren Spencer. And if you're not a PGE customer, you can contact your local utility to see what resources might be available to you. And now, before we proceed to the question and answer portion of the webinar, I'd like to remind you that you can continue to submit questions to me through chat, and I will ask them of Gary. And I'd like to move to the first question now, which is, Gary, is electrical PPE expensive?
Well, that's kind of a hard question to answer. It's all relative. In other words, compared to the injuries that folks can incur when they're doing electrical work or exposed to electrical hazards, no, I would call it relatively inexpensive. So for an example, I'll give you some examples. If a person was to get what I would call a 12-calorie, that's kind of a daily wear shirt and pants, face shield, balaclava, rubber insulating gloves with leather protectors, a full kit with a carry bag would probably run in the neighborhoods of let's say $400 for a full 12-cal kit. If you get into the higher energy level suits, the larger suits, they can range from, for a full kit, with the full hood and everything, from $600 there up. And sometimes people have their own kit for the lower energy levels. They may do shirt and pants or coveralls. And when we get into the larger arc flash gear, it just depends on whether we may have kits that people share depending on the usage, or we have people going in the field. Everybody may have their own kit. So you definitely have to budget for this. It isn't something that you're going to run out and, let's say, spend $25, $30 a person. It's going to be more expensive than that. But again, compared to the hazards and the cost of injury, it's inexpensive.
Thank you, Gary. And our next question is, my electricians have worked on energized systems for years. Why are there changes now?
Well, that's a good question. OSHA has had requirements to protect personnel against hazards to actually shut off systems, a lockout, tagout, and so forth for many, many years. But there is a increased emphasis, there's an increased focus that actually started in OSHA. And there was some major industry injuries and deaths that really triggered OSHA to start looking closer at this many years ago in the 2000 era. And that really started triggering a increased focus on protecting workers against arc flash. And of course, we have newer technologies that were introduced to the marketplace, such as the arc-rated personal protective equipment, the clothing that helps protect workers, that became available and became more cost-effective. So in a nutshell, there's an increased focus. And workers have been getting injured by this for years and years, but it just doesn't need to happen. We don't need to have the level of injury. And the level of injury across the U.S. was to the point where OSHA said, hey, we're having a lot of people that are getting injured by electrical burns and shock. And shock was already kind of an emphasis in many cases, but they have an increased focus on looking at protecting workers against shock and arc flash hazards. Thank you.
Thanks, Gary. And looks like we have another question here. I have a general lockout tagout program. Is that satisfactory for electrical lockout tagout?
That may be satisfactory. One of the things that we see in general lockout tagout programs based on OSHA 1910-147, if you based your lockout tagout program on 1910-147, you should really visit OSHA 1910-333 and look at the lockout tagout requirements, because electrical lockout tagout has additional requirements such as PPE for the electrical hazards that needs to be worn when verifying de-energized. They have requirements for verification that the electrical system is not energized with appropriate test equipment. They also have additional steps when tagout only is provided for. So in other words, if I can't lock it out and I'm doing tagout only, they have additional requirements that are not called for. So if you look at the OSHA requirements in 1910-333 for electrical lockout tagout, you see that they'll tell you that you can use a general lockout tagout program, but there are additional requirements that you need to implement that they show you in the electrical lockout tagout program.
Thanks, Gary. Next question, what voltage is the line between low-level risk and higher level?
Well, that's a very good question. A lot of times when we look at OSHA and NFPA 70E, they're typically looking at a 50-volt level. In other words, they think that they state that it's really by the standards, they're really talking about shock hazards above 50 volts. That doesn't mean we can't have shock hazards below 50 volts. In fact, in one of my training slides, I actually have a slide showing people that if you have cuts on your skin, your hands are wet, that you can create enough current flow through your body at a 30-volt source to cause enough current to cause a significant shock. So a lot of organizations I work with, they kind of set the threshold at 30 volts. In other words, they allow energized work with bare hands below 30 volts, but this is where OSHA and 70E kind of use the 50-volt threshold. This is a judgment call on your part. We have folks that allow their work to, them to work with bare hands up to 50 volts, but again, their hands have to be dry. They can't have any cuts or scrapes. So I'm more along the focused line of looking at the 30-volt threshold than the 50-volt, and you'll see that in NFPA 70E, in the back of 70E, in the work when they talk about work around adjustable speed drives. So I'd probably say, under the right conditions, even, 30, 35 volts can be hazardous.
Thanks, Gary. And I believe this is our last question. Do I have to comply with OSHA and NFPA 70E requirements?
Okay, well, in regards to OSHA and 70E requirements, OSHA, yes. OSHA, is an agency that they send inspectors out, and that's mandatory that all employers comply with the OSHA requirements. So it's very important you know and understand the OSHA requirements. Now, 70E is an industry consensus standard. It's not mandated to have compliance with NFPA 70E. Although, again, OSHA references the standard to provide information that can be helpful in complying with the OSHA requirements. And I would highly recommend you look at it and use it, but it doesn't mean you have to. It's mandatory that you comply with all aspects of it. Now, you might want to just from protecting personnel against hazards and injury, but again, there may be some sections where maybe you come up with alternative methods as compared to what 70E has that provides the same level of worker safety. So again, OSHA hasn't mandated it that you follow 70E. You do have to follow the OSHA requirements, but OSHA gives you some flexibility, but they do point you towards 70 as providing information that can be helpful in complying with their requirements, but you can also come up with alternative methods.
Thank you, Gary. That was the last question, and thank you all for joining us today.